Hi, I'm Professor David Farina. In today's lecture, we're going to talk all about telescopes and specifically looking beyond light. So, telescopes, but not light? How is that even possible? Let's get started. So, the first type of non-light observatory, I should probably clarify, this isn't a traditional telescope as you would think of it, but it is an observatory of a telescope nature. We're using particles now as a way to start to do astronomy, and this is extremely new. One of the new things that we're doing is looking at something called cosmic rays. So what ends up happening is we've got particles from somewhere out there, the sun, a supernova, in some cases, places we don't even know where they're coming from, object types we don't even know where they're coming from, and these cosmic rays hit Earth's atmosphere, and when they do, they produce a shower of secondary particles. If you're familiar with the collision of particles within a particle accelerator, a collider, this is a similar process that happens naturally. So what we do is we see these particles are showering down, and by the way, this is happening all the time around you. You can't see these particles. They're moving at a high rate of speed, and they are well beyond the size. They're way smaller than a single atom. So you can't see them, but they're happening all around you right now. And when these particles pass into the atmosphere, they hit the atmosphere, they break apart into their subatomic particles, and they shower down upon our detectors. So Earth is constantly being bombarded by these. And it's not really well understood where all of this is coming from, as I already stated. But how do we detect them? We detect them through a process of coincidence. Yeah, like a coincidence. A coincidence. We've got something called a scintillation paddle. These are basically pieces of plastic that have the ability to transmit signal in the form of a small electric charge that sees when a particle hits the scintillation paddle. A second scintillation paddle is placed underneath. If both paddles sense a particle hits them together, a coincidence, then we know that it had to have been a cosmic ray. So when a cosmic ray, these subatomic particles that are showering down upon us, in fact, hits the scintillation mechanism, the energy is transferred along a cable into our coincidence logic board, which can then go into a computer system and be interpreted as data. Now, a second type of non-light astronomy that's being done is through neutrino detectors. This is a different thing now. Neutrinos are particles that are produced by our sun. They're produced by all stars in the sky, and we don't quite know how they work. Neutrino has 3 different flavors, and those 3 different flavors, kind of think about it like different flavors of ice cream. What's your favorite type of ice cream? Okay, so let's have just Neapolitan, let's say. We've got chocolate, vanilla, and strawberry. I'm not a huge fan of anything but chocolate. I mean, chocolate's the best, of course. So I'm going to go into the refrigerator. I'm going to pull out my Neapolitan ice cream, and I'm going to scoop out a big scoop of chocolate ice cream and put it in my bowl. Here's my chocolate ice cream, and I'm eating my chocolate ice cream, and as soon as I put that chocolate ice cream in my mouth, all of a sudden it turns into strawberry. Wait, what? I thought I started with chocolate. I got it out of the refrigerator. I scooped out the chocolate. I know it was chocolate. It was chocolate. But now it's turned into strawberry. See, that's how neutrinos work. Fortunately, ice cream does not work this way, but if it did, you get the idea. So neutrinos come in 3 different flavors, and they can change flavors at random. So one of the things that we need to do is we need to understand, how does a neutrino work? Neutrinos can actually pass through the Earth and out the other side without ever hitting anything. Yes, through the Earth, out the other side, and they somehow found their way to squeeze through every little atom in the Earth. That's because they are weakly interacting particles. They don't really interact with normal matter like we would normally think. They just pass right through. So we need to produce something to catch them. So what we do is we build our systems for neutrino detectors deep, deep underground. And this particular one is found in Japan. And so they have a mountain. It's about 1,000 meters high, and deep, deep below the mountain, we've got a access tunnel drilled in here. A detector hall is found right in the middle, and they have these photo detectors, these light sensors. Now, right now you see these guys sitting on this boat, and they're just kind of floating on this pool of what effectively is cleaning solution. They're currently draining this so that they can work on the detector. When in use, this thing is filled all the way up to the very top with this cleaning solution. Now, this is where the cool stuff happens. So as a neutrino hits this cleaning solution, it produces a little bit of light. And what happens is these photodetectors, these little spheres inside of the neutrino detector, see that light. And we have a neutrino detector. Now, other neutrino detectors are being built throughout the world. This one is being built in Antarctica. It's called IceCube. And IceCube is basically a bunch of drill holes, deep cores, that we then produce our little digital optical module. We drop that down in here, and we can then determine neutrinos have been detected because we have all that overlying ice keeping any other type of particle from reaching it. So the only thing that could get there is those weakly interacting neutrinos. And let me back this up. There's a string of these little digital optical modules, and on each string there are 60 of these as they've dropped it down into the IceCube detector. So think it's one string has 60 detectors, and you make an array. So once again, there are 3 main different types of neutrino. There's a muon, a tau, and electron neutrino, and they can switch between those 3 different types at random. Just like this. 3 different flavors of neutrino. The newest type of detector is called a gravitational wave detector. This is something that actually was hypothesized in the early 1900s with Albert Einstein. Einstein and his theories of relativity hinted at the fact that gravitational waves, if his theories were correct, which they apparently are, would be able to be detected. But not up until the very recent future, within the last few years, have we been able to actually make an instrument sensitive enough to detect a gravitational wave. Welcome to LIGO. LIGO is the Laser Interferometer Gravitational Wave Observatory. And LIGO is actually not just one, but it's actually 2 different facilities. Here's how they work. So LIGO is sending a laser beam down a tunnel through a beam splitter. Now, a beam splitter, remember, is going to take a single beam of light and split it perfectly into 2 separate, even and synchronized, this is important, synchronized beams. Those beams now travel at near the speed of light to the other side of the detector, which is many meters away. 4 kilometers to be exact, 4,000 meters. And as it travels down, it hits the mirror on either end, and then it bounces back, hits the beam splitter again, and is sent to a detector. Now, if the wavelengths of these two beams now are not synchronized, then we can detect a gravitational wave. In other words, if the gravitational wave is moving in this direction, then one of the detectors is going to be stretched in one direction, the other leg of this is going to be stretched in the opposite direction. And so as a result of the wave front passing, we have the light being bent or warped by the space and time effects of Einstein's relativity, which then produce an interference pattern on our detector. Okay, and I know those words right there were a little bit more technical than you're used to from me, but I don't really have an easy way to make this very simple. So if you have questions about this, please know that this is well beyond the scope of our normal discussion, and I'm just trying to give you the coolest and newest thing. So LIGO comes in two main facilities. They're the Livingston and the Hanford facilities. And what we're looking for is a coincidence between these two facilities. In other words, if we detect the gravitational wave signal at both locations, then it's real. Because there are some other noise issues, just like any telescope, where we have a truck drives past and causes the ground to shake, and the one detector might go off even though it wasn't real. This way we keep the two facilities extremely far apart. Here they are on a map. Here's LIGO Hanford and LIGO Livingston. They're significantly far enough apart that there really should be no way that they're both detecting the same thing in the time interval that they're able to see these wave fronts. So remember, at the speed of light, the speed of light can go around the Earth 7 times in a single second, 7.5 times in a single second. So these two facilities are getting nearly instantaneous results of that detection. So even if something were to happen, like an earthquake, for instance, that takes a lot more time, and they could determine that that was something that was an anomaly, versus a real detector, real detection, I should say, where the images or the data are found within rapid sequence of each other. Notice there are other gravitational wave facilities throughout the world. There's LIGO India as well. And there's a number of other facilities that are either under construction or operational. So this LIGO India is planned. It's not even under construction yet. But if we were to have a LIGO India, we would get yet a third coincidental detector, and that would improve our signal to noise ratio. In other words, we could see the data comes above the noise and the noise goes down, which means we get more detections, easier to filter out the noise. So I hope you enjoyed our discussion today on telescopes and specifically looking beyond light. This new style of astronomy is fascinating to me, and I really hope that you look into it more. This is the next step in our journey towards looking into the universe in a completely new and fascinating way. Thanks for sharing your time with me. If you like this video and you would like to learn more, please click the like button and subscribe at the bottom. And if you'd like to get a notification each time I make a video, click that little bell so that you find out. Thanks a lot, and have a stellar rest of your day.